Hello and welcome to this Chemistry World webinar. My name's Philip Broadwith and I'm the business editor of Chemistry World. This is the recorded version of a webinar first broadcast on the 17th of August 2021 entitled Moving Beyond Spreadsheets, Rational Design of Materials Using Advanced Informatics and Machine Learning. If you were to have attended this webinar live rather than just the recording, you would be able to interact with our experts and ask them questions. But the next best thing is to watch this recording. You get all of the information that was presented by our experts from Schrödinger. Today's topic is looking at how to use machine learning and more computationally demanding physical modeling side by side to design new materials with the properties that we might want. In this case, we're looking at organic light emitting diodes, or OLEDs. We're trying to create predictive models to work out new families of materials, predict their properties, and, for example, the molecular volatility. We've worked with Schrödinger to bring you this webinar. They help us to find topics that we think you guys might be interested in and put us in touch with the right people to come and tell you all about it. So today's speaker is Yuling An. She is the product manager for machine learning and informatics for materials science at Schrödinger. She's a background as a computational chemist and has a wealth of experience at Schrödinger developing software for a whole range of different applications, including protein structure prediction and cheminformatics. And now she has overall responsibility for machine learning and leading product development in the materials science area. Over to you, Yuling.
Thank you. Thanks for the kind introduction. Hi, everyone. Thanks for joining us today. I'm really excited to present some of our recent studies in applying machine learning for material design on using our material informatics platform, LiveDesign. So in the past decades, with the advancement of algorithm and the increasing power of computing resources, we have seen a wide adoption of physics-based simulation at atomic and molecular level in almost all aspects of chemistry, from drug discovery to material design. These simulations can be used to provide high accuracy predictions of various properties for materials and process controlling energetics, which in turn helps targeted precision design of new materials and processes. In Schrödinger's material science suite, our physics-based simulation tools include QM, DFT simulations on molecular systems, from OLED material to catalysis, but also MD simulations on, for example, polymeric systems with solvents, with iron or additives. In the meantime, especially in recent years, as we start to realize the value of existing data, either from experiments or from simulation, statistical analysis and machine learning approaches have shown great potential in exploring much larger design space, either chemical space or process parameter space. Machine learning models also allow us to evaluate millions of compounds or formulations rapidly, something that would be hard to accomplish either by experiments or even by physics-based simulations. So a key strength of machine learning is its ability to extract the underlying structure property relationships, leveraging experimental and computational data. And as more data is being generated from simulation and experiments, the potential of machine learning approaches in material discovery and design is only going to get bigger. However, in order to realize the great potential of machine learning, data needs to be put into a central place, organized and analyzed in such a way that it's easy to understand and easy to share. That is where the informatics platform solution comes into the picture. It not only allows live sharing of data and design ideas for rapid decision-making, but also easy access to expert physics-based simulations and machine learning models. Another key to the importance of successful informatics platform is enabling collaboration, whether from multiple divisions of global organization or from scattered geographic locations these days. So with that in mind, I'll present our recent study of using the generative machine learning model for the designing OLED, especially whole transporting material with target property profiles on LiveDesign. So OLED, I think everyone here probably is well aware that is a fast-growing market, especially in the past year or two. So it's been commonly used for smartphones, different lighting devices, fitness devices, not to mention TV, or in auto industry. So based on recent forecast from Verified Market Research, the global OLED market, for in 2020, that's over almost 28 billion. And the compounded annual growth rate is predicted to be around just below 14%. And so that means by 2028, the next 5 or 6 years, that will reach threefold more. So this is obviously an exciting and huge market to explore, but there are also obviously challenges, especially when we look into developing new OLED materials. So one big challenge is the vast chemical space to explore. The traditional try and error approach is obviously expensive, time-consuming, and often ineffective. So within Schrödinger Material Science Suite, we actually have a whole suite of high-throughput atomic scale simulation that can help on the simulation side to provide comprehensive solutions. And that includes, for example, multi-stage QM analysis, optoelectronic screening, using bound dissociation energy to predict stability. Also on the excited state analysis to help you to get better design ideas. So that's on the simulation side. But with machine learning, for example, both on the supervised QSPR type of machine learning models or more advanced generative machine learning models, these will also help in great deal to design new OLED material. And once you put the physics-based simulation, machine learning on the material informatics platform, we can make the whole discovery process smooth and effective. So the idea behind our in this study is we try to develop a chemical library, firstly from a commercially known OLED material in the whole transporting layer space. And from these collection of known OLED materials, we actually derive two components of the information at the chemistry level. One is to understanding what would be the common core structures in this space. And the other is the R group library. So from the R groups, we apply genetic enumeration that involves, bond crossover, fragment mutation, and also includes, element mutation. And by using our symmetric enumeration tools, we can combine the extracted common cores from the known OLED space with these enhanced R group libraries to build over 2 million compound OLED-like compound chemical library. And that will help us to define what is a chemical space. Our machine learning methods will be looking into to design new material. So once the chemical space, we understand the chemical space we are looking into, the next thing when we design material in general is we're hoping that it will have the desired property profile. And in this case study, we are looking at some of the most important optoelectronic properties that are critical for these type of materials. So here we're including 3 optoelectronics properties: HOMO energy, LUMO energy, and hole reorganization energy. In addition, we also understand the thermal stability of the materials is also very important, especially when it's embedded into devices. So for that, we're looking at the glass transition temperature of the material. And for the glass transition temperature, instead of using the physics-based simulation, because it's can be really expensive on such a huge data set, we actually used a pre-trained QSPR model for making glass transition temperature prediction for the chemical library, the compounds in the chemical library we developed. And this model was built from published literature using our machine learning tools to build a very predictive model. So now we are looking at 4 properties, and this plot it shows this plot was actually generated from, inside LiveDesign, and you can see in the scatter plot the x-axis is HOMO energy, the y-axis is LUMO energy. But besides that, we can also do color encoding. For example, for the hole reorganization energy to expand the dimension from the scatter plot. So in this case, the color green color is lower hole reorganization energy, below 0.2 EV, and the red color is showing is higher hole reorganization energy, above 0.4, and somewhere, orange, yellow is somewhere in between. Besides color, we can also add an additional dimension, such as the size of the data point to correspond to another property. And in this case, what we're showing here, we're using the TG value, the size of the based on the value. So the smaller the dot you see, it's lower TG, and the bigger the dot, the higher TG. So in this plot, even though it's still a 2D scatter plot, but by encoding color and size of the data, we can incorporate a much richer information in this scatter plot from LiveDesign platform. So since I have been mentioning LiveDesign a lot, and most of our study was actually carried on LiveDesign as well, so I'll use this opportunity to give a quick overview of LiveDesign and to demonstrate how it made our life easy when dealing with millions of structures and multiple properties from sophisticated calculation and machine learning models. So what is LiveDesign? LiveDesign is a web-based material informatics platform. It can be a central place for store and manage both experimental data and computational modeling. It's web-based, which means the data imported into LiveDesign will become instantly live to all its users. So from a user perspective, all they need is a browser to open LiveDesign. It is scalable. So LiveDesign has been used for global organizations with tens of millions or even hundreds of millions of compound. But also it's flexible and robust enough to satisfy the specific needs of smaller or medium-sized customers. It has the latest informatics tools to support data analysis and data visualization. And by bringing everything into a central platform, all data into a central platform, it will provide a lot of critical insight back to its user to understand, to make use of their data. So besides the data part, another big advantage of LiveDesign is it's a platform where a user can port or develop new workflows on LiveDesign and run the computational tasks on it, so that the computational results will come back side by side together in one spreadsheet, or we call it live report, with their either imported user data or experimental data. And so these tasks can include machine learning models or simulation, QM property calculations, and all together, by bringing all data into a central place, this LiveDesign platform is really our core, to support material design, drug discovery, any advanced computational chemistry to needs, and to satisfy customer digitization needs. So here, this is the example of a live report we used in our study. So here we have our training data, and this is about 1,000 structures that we picked from diversity selection from the over 2 million chemical library I mentioned earlier. And these structures have gone through optoelectronic calculation to with DFT to get their HOMO-LUMO energies and whole reorganization energies, plus the predicted machine learning predicted glass transition temperature. So in this live report, you can see the first column is a 2D rendering of the structure, followed by ID. The next two columns, this is a machine learning workflow, or we call model in LiveDesign, which the output from this calculation is, one is, you can see the prediction, which is the predicted value, the predicted glass transition temperature of each structure. But in addition, because this particular machine learning model we built, it also enables us to visualize at atomic level what atoms or fragments made positive or negative contribution to the property. So we can embed the visualization of the model or the annotation of the structure as an image into the live report together with the numerical value. And the next couple columns, next three columns are the whole reorganization energy, LUMO energy, and HOMO. So now when we have all this data in live report, because in our goal in this study is to use machine learning to generate structures, not just with a best single property, but a combined property profile of all these properties together. So in LiveDesign, a very convenient way to do that is what we call multi-property optimization, or MPO, which can combine an arbitrary number of properties into a single numerical value that is always between the range of 0 and 1, with 1 being the best, satisfying all the criteria user specified for the properties, and 0 means the least. And once this MPO column score is set up on LiveDesign, the columns are automatically colored in such a way to provide visual hints to show what are the structures that best satisfy the user-defined conditions. And green means good, a red means bad, the orange, yellow, somewhere in between. And so not only the MPO column is colored, but any of the properties that are included in the MPO calculation will also be color-coded in a similar way. And here I'll show you in LiveDesign, this is a screenshot taken directly from LiveDesign, how the feature allows a user to really have the control, can set up the customized thresholds of how they like the property to be optimized. So for example, in our study, the homo energy, we're trying to set a target value of minus 5.5, in this case 5.7, and in this case you can specify both the inner tolerance and the outer tolerance of the target value. So you can define how narrow or how wide the peak is. And we also can define for example, if for the lumen energy, we're maximizing to make it less negative. And in this case, you can specify what are the thresholds that should be good, and which is what would be considered as bad. And basically, you can define how steep or how slow the curve goes up. And similarly for whole organization energy, where I want to minimize it. And so here, what the user can define. So for example, if it's below 0.2, and that's good. If it's above 0.4, it's bad. And for glass transition temperature, we want to maximize it. And so here we're setting, if it's above 140 Celsius, it's good. If it's below 110, it's considered as bad. So not only LiveDesign MPO can include multiple properties, it also allows user to to assign weights to the properties. So by default, all weights are equal to 1, but a user can easily adjust what will be the properties they would like to, the weight of each property they want to set. So besides LiveDesign, we understand, especially in material science, a big challenge is there are so many different types of systems, polymer, small molecule, periodic solid structures, not to mention formulation. And so LiveDesign is built to be able to support this very diverse kind of chemical systems, from polymers, small molecules, OLED material, or catalysts with metal complex, or formulations where it's a mixture of data, and also even for things that without structure, for example, the processing conditions or experimental conditions. So now let's go back to our machine learning part. The machine learning protocols, the generative machine learning model we're used in this study is based on a previous publication in the drug discovery space. It's called REINVENT framework. So the idea of it is to use reinforcement learning with a recurrent neural network on the SMILES representation of compounds. And so the idea is first, trying to learn the chemical space, and that's prior network. And in the original study, because it's for drug discovery, I was using the Campbell database to learn chemistry. The other part is now, how do we know what kind of property the machine learning model should generate? And that is we call the scorer network. And so this one is a second training data to provide property training for the machine learning model. Now, with both the chemical space and the scorer training, the property training, the agent network is able to generate molecules, structures that is in the chemical space with the targeted property. And as you can see, this workflow has a lot of potential to be adapted outside drug discovery by learning different chemical space and different property scorer networks. And that's basically what we did in our study. Using the same REINVENT protocol, we use the enumerated structure, the over 2 million enumerated OLED-like structure as our chemical space. Then we selected using chemical diversity selection in our Schrödinger tools. We selected a subset of just below 10,000 structures, over 8,000 structures, and these structures fit into the neural network. For the training set, as I mentioned earlier, we're considering 4 different properties. We have the whole reorganization energy, scale HOMO, scale LUMO, and the machine learning predicted glass transition temperature. Once we feed into the information into the machine learning model, it was able to generate over 56,000 candidates with targeted property. So remember what I mentioned earlier, we used MPO, the multi-parameter optimization score, to combine all 4 properties into an easy to understand, easy to optimize single numerical value. So with MPO score, we always want to maximize, because maximizing it is meaning we are trying to satisfy all the properties to the condition, either it's target value or minimize or maximize in individual property level. Now, once we are looking at these generated candidates, it not only gives us the structure, but also a predicted score of these structures based on the scorer neural network that is fed into it. And the score is in the same scale as a arrangement MPO score. So majority of these generated candidates have a MPO score, the predicted MPO score of above 0.8, which is considered as high. So from that, we did a diversity selection again, and to select a validation set of just below 2,500 structures. And these, in the next couple of slides, we'll be looking at the validation set, which is from machine learning generated structure. And then we run optoelectronics property calculation, followed by MPO score, so that we can compare these machine learning generated structures with the original training set, because they are calculated the same way from on the simulation side. So here, this is the overall comparison between the validation set, which is red, and the training set, which is blue. This is the looking just at the MPO score, the calculated MPO score. Now, because we redid the calculation on the machine learning generated validation set. So now, if we look at just look at the blue, which is the training set, we can see the x-axis is the MPO score is from 0 to 1. we can see the training set, the structures actually pretty much evenly distributed along the property profile spectrum, the range. However, when we look at the validation set, you can see it's all very concentrated on the right-hand side, which is the maximum side, which is the one we want. So now this plot was very exciting to us. We are really happy to see the machine learning generated structure overall gives much higher concentration of desired property, the combined desired property. So now numerically, we can see in among the training set, just over 16% of the structures have MPO score above 0.8. So we'll consider 0.8 to 1 as the optimal MPO score. That means the structures have optimal properties. In the machine learning generated validation set, we can see 84%, more than 84% of the designed structures have the high MPO scores. So that's very exciting to us. Now we're going to look at the individual properties, how do they compare between the training set and validation set. So first we look at the Homer energy that we target at a specific target value, and we can see within that range, the validation set is 86% compared to 32% in the training set. The novo energy, this is actually interesting because they're similar. Because if you remember, when the original training set was actually combined, selected from a large enumeration chemical library that came from the known OLED material core with varied R groups. So our starting point of structures actually pretty reasonable. And if you look at the next couple of properties, so for example, in the whole reorganization energy, the percentage of the validation set that is almost 71% compared to 36% in the training set. And also in the glass transition temperature value, you can see the peak is very obviously shifted to the right-hand side because we want to maximize the glass transition temperature. So we can see in all the 4 properties we're considering, 3 out of 4, the machine learning validation set clearly have a much more advantage in terms of the property, the optimized property, with 1 lumo energy that is pretty much followed the same as a training set. So that's why overall, the combined property profile from the machine generated validation set is much more optimized, have a lot more higher percentage of optimized structures. So now the next thing we are trying to look at, before we are looking at the properties, we are just looking at the machine learning generated properties. Great, they all generate really nice property profiles. But now another thing we want to look at is whether or not the structures, machine learning generated structures, have some similarity from the training set. Because ideally, what we want is, we want the machine learning generated structure more or less in the same chemical space as the training set, but with better property profile. So to do this, we sort the validation set by calculate MPO score. We take the top 500 structures. And for each of the 500 structures, we find the most similar structure in the training set. Now, we compare the calculated MPO score of the pair. And ideally, what we are hoping to see is the machine learning generated candidate fall within the same chemical space as a training set, meaning the structure similarity between the pair is reasonable. but it has a better property profile, meaning we're hoping that the machine learning general structure will have a higher MPO score than its corresponding neighbor in the training set. So now, next slide, I'm going to show how did we do. Before I jump to that, this is I want to give you an idea of how we did this in LiveDesign. So once you have the previous slide showed you have data and you can put it in a spreadsheet, but as you have more and more data, it's become, you can easily have hundreds of columns in a spreadsheet. It becomes very tedious to scroll back and forth. But in LiveDesign, we also have a different way, more customized views for user to pick exactly which property to show, and using the plotting tools that can incorporate, color and size and even shape, and using, synced with selection, so you know which, when you look at the data point, you know exactly the property and the structure of the compound you're looking at. So with the plotting tools, we're able to looking at the results to do our structure and property similarity analysis. In this plot, what we are showing is the y-axis is the difference in MPO score, in calculate MPO score, between one of the 500 top machine learning generated structure with its closest neighbor or closest sibling from the training set. So if the difference, the delta MPO, is positive, that means machine learning generated structure has a better property profile than its closest sibling in the training data. And the x-axis is the Tanimoto similarity between the pair. And you can see the range is from 0.5 to 0.8. So they're reasonable, indeed have reasonable structure similarity. And you can see anything above the red line is the MPO score. The delta MPO is positive, meaning it's better. The machine learning generated structure is better. And this histogram is another way of actually viewing the same data, where it's being binned. The difference in MPO score is being binned, divided into these bins. This is the difference is by 0.05 all the way to the difference larger than 0.3. And so overall, over 92% within these 500 machine learning generated structures have a more desired property profile than its nearest neighbor in the training set. So we are really happy to see the results. So here, I just want to give you a quick view of glance of some of the structures, machine learning generated structures. And so here on the left is machine learning generated structure with the properties, and the calculate MPO score is 0.94 compared to its closest neighbor in the training set that has MPO score of 0.733. And the MPO improvement in this case is over 28%. And so here's another pair, similar story. This is on the left is the machine learning generated structure. On the right is nearest neighbor in the training set. And again, here we see MPO improvement of over 21%. So now I'm going to jump into our second study. This is about volatility predictions for organics and organometallics with machine learning. And so we can all familiar with the importance of volatility property especially in recent years in industry, that it's very important property for any kind of process that is related to nanoscale thin film deposition process, either the CVD or ALD. And a key factor in this process is being able to selectively allow the wanted precursor compounds to vaporize and continuously drawn into the deposition chamber. Well, the unwanted volatile components can be removed by reduced pressure or inert gas purge. So knowledge about volatility of a diverse set of precursor-like compounds is critical. However, volatility is also hard to measure experimentally and expensive to calculate even with physics-based simulations. Because of the complexity of the surface reaction, especially at various process conditions. So this is an ideal case. Machine learning could help. So the training set we looked into. The first one is we're only looking at organic training set structures. This is including over 1,000 organic molecules containing mostly non-metal elements. And these are, from these over 1,000 organic molecules, we actually collected over 12,000 experimental data points at various pressure and temperature. And the pressure range is actually covers a really wide range of pressures, from 1 torr to 30 atmosphere. So we generate molecular descriptor and fingerprints. And in this case, we use the log P were used, and the machine learning model was trained to predict the inverse of temperature. So here's the result, and the top performing machine learning algorithm we found in our study for the organic compounds is the light gradient boost machine, and the other one is multi-layer perceptron. And so the RMS arrows, of course, the model based on square mirror is perfect, almost perfect. And even when we're looking at the RMS arrows is well below some of the publications from either machine learning model or previously. So we're very happy about this machine learning model. And we also tested this model using compounds that are outside the training set. And so here we have 4 different structures we used. We did not include in the training set, each with a different color. So what you can see is the dots represent the experimental values, data type at different temperature and pressure. And the dashed lines are the machine learning predicted values. And as you can see how well they match. So we are really happy about the high quality machine learning model we were able to build. Now, with that, we actually went one step further, which is we know the organometallic complex is very important, very commonly used, and it's even more challenging both from a simulation perspective and from previous machine learning models. And for this one, the big task is to collect enough high quality data. And so here, with the help of our data team, we managed to collect over 3,000 experimental pressure temperature data points. And we include inorganic descriptors in material science suite to develop machine learning model. And in this one, the machine learning model, we eventually, the best machine learning model we eventually end up with is actually ensemble machine learning model. It's a combination of neural network and light gradient boost machine. And so the model, looking at the results of the model, you can see it's still very good. However, the RMS arrow is slightly higher than for the organic data set, although it's still on par with the publication even for the organic data set. So here we believe this is also a model that can have a lot of real world commercial value, and we are happy to share the results with everyone. And another interesting is because we have a relatively spread out data collection, so we want to see, based on the number of compound data point that covers all the elements in the periodic table, we can see the RMS arrows within that subgroup. So here, the darker brown shows the more data collected around the elements, and lighter, gray means very few. So it's very interesting, or as expected. When you have more data points, you can see the error is lower, and when you go to things like fewer data points, the error goes up. So this kind of it's a validation of general machine learning principle. Yes, it'd be great we can have the more data we have, but we also understand the quality of data is very, very important. So we have this, the volatility machine learning model. We definitely believe it can be used in many different areas. So I mentioned ALD, CVD, but also in OLED material development, or even in food substances, and to study the headspace, for example. And in oil, gas industry, membrane separation, and exploring hazard studies. So we will continue working on this, getting more data in different application area and systems. And so we hope this will really provide a lot of value. So summarize, I presented our goal-directed generative machine learning model. It was able to create a new set of whole transporting OLED candidates with improved property profiles. And we were able to combine multiple properties into a single MPO score that resulted in improvements in all individual properties. The physics-based simulation and machine learning really complement each other, as you can see in this presentation, to speed up materials optimization and design. And machine learning, I hope I can convince you that can really provide significant value in predicting hard to measure or expensive to calculate properties. And the technology presented here, is applicable to material design in many different areas. Thank you. That ends my presentation, and I'll be happy to answer any questions if you have.
That was Yuling An, the Product Manager of Machine Learning and Informatics for Material Science at Schrödinger. A big thank you to Schrödinger for sponsoring this webinar. It's part of a series that we're doing in Chemistry World with Schrödinger throughout 2021. If you want to find out more about the webinars that are coming up, please go to chemistryworld.com/webinars. And if you want to find out more about what Schrödinger is doing in the field of material science, then there's a website there on the holding slide at schrödinger.com/material science. Thank you all for coming and watching this recording, and we hope to see you at some more Chemistry World webinars in the future. My name's Philip Broadrith, and I'll see you again soon.